Yeah, so thank you all again. So I'll be telling you about sort of this technique that my collaborators and I have been developing over the past few years called spectral independence, and I'll hopefully also tell you a few of a few highlights for applications. So the main question, the main problem that we're going to be studying in this talk is the following, which I'm sure you're all familiar with. So you're given some high-dimensional probability distribution mu, and your goal is to efficiently sample from this distribution. And as I'm sure many of you know, since this is the Monte Carlo seminar, this task sort of is a fundamental algorithmic primitive underlying many applications, for instance, to statistical estimation, to statistical inference, and also even to optimization, just to name a few such applications. Okay. Now, in this talk, we're going to be focusing on sort of the discrete setting. And as sort of a running example, we're going to be focusing on the problem of sampling graph colorings. Okay, so recall a graph coloring is an assignment of colors, 1 through q, to the vertices of some graph G, such that neighboring vertices are not allowed to have the same color. Okay? And the goal is to, given the graph G and the number of colors q, sample a uniformly random coloring of the graph. So graph coloring is sort of one of these quintessential sort of constraint satisfaction problems that is extremely well studied in combinatorics and theoretical computer science. And also this problem of sampling graph coloring actually arises in statistical physics. So the technical name for the uniform distribution over graph colorings is sometimes called the Potts model, or the antiferromagnetic Potts model. Okay? So sampling graph colorings is going to be sort of our running example throughout this talk. Now, there's a very simple and very natural Markov chain you can run for sampling graph colorings called Glauber dynamics, or sometimes also called the Gibbs sampler if you come from sort of the machine learning side of things. And the basic idea is to start from some arbitrarily chosen coloring, maybe the one here, and to iteratively make random local perturbations to this coloring. So in particular, Glauber dynamics sort of evolves as a Markov chain, which evolves as follows. In each step, I pick a uniformly random vertex, let's say this highlighted one here. And then I look at sort of the colors assigned to its neighbors. These are the colors that I'm not allowed to use. And then out of the remaining colors, I'll pick one uniformly at random and then recolor this vertex. So maybe now I set it to blue, for instance. Okay? And then I just sort of repeat this two-step procedure over and over again, right? So then maybe now I pick this color. All of its neighbors are blue. So I just need to pick a uniformly random color which is not blue, and then recolor this vertex. So maybe I color it red, for instance, and so on. Okay. And I want to emphasize that sort of Glauber dynamics is actually an extremely general scheme for sampling from high-dimensional distributions, which have sort of this like product-like structure where there's sort of coordinates. And basically, it just evolves as follows. I pick a random coordinate or a random vertex, and I resample the assignment for that coordinate or vertex conditioned on the remaining assignments. Okay. And if you'd like, there's even a very nice formula for this. Okay. So this is a very easy to implement Markov chain, just a few lines of code. And sort of the key question or the key quantity we need to study regarding this Markov chain is its mixing time. Namely, the number of steps t that you need to run this Markov chain, such that you are guaranteed that the distribution of where this Markov chain is at that time step t is within, say, epsilon of your desired target distribution mu. Okay. And typically, this distance will be taken to be something like total variation. Okay. And so the key question is, how can we bound this mixing time? When is it upper bounded by a polynomial in the size of the input? That would be sort of sufficient for quote unquote efficiency, at least to a theoretical computer scientist. And also, maybe when is it linear in the size of the input? That would be sort of a more practical notion of efficiency. Okay. So our goal is to analyze sort of the performance of MCMC algorithms, and there's sort of a few criteria we would like from our analysis, right? So first, we would like the analysis to be sort of not ad hoc, or more precisely, we want we want there to be some kind of flexible and unified framework that is capable of tackling a wide variety of Markov chains and sampling from a wide variety of distributions. At the same time, we want sort of the framework to be sort of conceptually simple, whatever that means. But hopefully, the framework would provide some kind of intuition for why the Markov chain is mixing rapidly. And third, we want ideally for the framework to provide nearly linear time guarantees. Okay, so practical performance guarantees. Okay, so this is sort of the three criteria we would like to aim for from such a framework. Okay. So this is the outline for the rest of my talk. So first, I want to sort of tell you about a couple of applications of this spectral independence framework. And then I'll tell you about what is this spectral independence framework. And then I'll sort of provide a sketch of the analysis for the special case of graph colorings. And then I'll conclude with some future directions. Okay, so maybe let's start with a sample of applications, no pun intended. So the first application is to this problem of sampling bases of matroids. Okay, so a matroid is just a family of sets or a set system satisfying a certain quote unquote exchange property, which I won't define formally, but it will suffice for our purposes to keep in mind two representative classes of examples, namely the set of spanning trees in a graph and the set of linearly independent bases of vectors in a vector space. So the problem is to sample a uniformly random basis of a matroid, or if you prefer, sample a uniformly random spanning tree in a graph, or sample a uniformly random linearly independent basis of vectors in a collection of vectors or a vector space. So the problem of sampling bases in matroids actually has abundant of applications and connections, in particular to the reliability theory of error-correcting codes and networks. And it even has connections to problems in machine learning, such as determinantal point processes. Okay. But let me just spend a couple slides sort of sketching sort of the connection with reliability theory. So imagine you have a graph representing a network, let's say a communication network or like a road network. And now each link of this network can fail. And let's say it fails with some probability p independently for each edge of this graph. Now, a fundamental quantity you might want to know is, what is the probability that this network remains connected under this failure model? So the goal is to be able to compute this probability. And it turns out you can do this if you can sample a uniformly random basis from the matroid associated to this graph. So that's an example of an application to network reliability. Let's also see an application to the reliability theory of error-correcting codes. So imagine you have an error-correcting code that is described by a parity check matrix H. Okay, so the code would look like the set of vectors X, such that H times X is equal to 0. And now suppose you send your code word through a noisy channel, and each bit of this code word gets erased independently with some probability p. Now, again, what would you like to know is, what is the probability that you can uniquely recover the correct code word given this noised up message? Okay. Now you can do this if the columns corresponding to the erased bits are linearly independent, because then you can sort of solve a linear system. And so you can compute this probability if you can count the total number of linearly independent subsets of columns of this matrix H. Okay. And this turns out to be equivalent to sampling a uniformly random basis, sampling a uniformly random basis from the matroid described by these column vectors. So motivated by these applications, so this problem of sampling matroid bases has been the subject of intense research for several decades. And unfortunately, most of the prior works have only managed to address very special classes of matroids, such as spanning trees. Now, in 1989, Mihail and Vazirani conjectured that a certain very natural Markov chain actually successfully samples the uniform random basis in polynomial time. Okay? And actually, this Markov chain is actually very simple to describe. It's very simple, similar to Glauber dynamics. What it does is the following. Let's say I'm looking at spanning trees. If I'm at some specific spanning tree, then what I do is I remove a uniformly random edge. And then out of all edges that I can add back to create a new spanning tree, I pick one uniformly at random. Okay, so this is sort of like a random swap Markov chain. And the conjecture was that it mixes in polynomial time. And with my wonderful collaborators, Nima, Cheyenne, and Cynthia, we managed to make this 30-year-old conjecture into a theorem using the techniques that I'll describe later in this talk. And maybe I also want to mention that since then, using more sophisticated techniques, we also managed to bring down the running time. In particular, we now have nearly linear time samplers based on this Markov chain. And this currently yields, for instance, the fastest known algorithm for sampling spanning trees and graphs. And it also extends to a very natural discrete analog of log concave distributions. So our second application is to the problem that I mentioned at the beginning of this talk, which is to graph colorings. Okay, so just to recall, a coloring is an assignment of colors 1 through q to the vertices of the graph, such that neighboring vertices do not get the same color. And this sort of the problem of sampling graph colorings has many applications in theoretical computer science and to statistical physics. Now, so there's this big conjecture in the field of approximate counting and sampling due to Mark Jerrum from 1995, which says that if the number of colors q exceeds the maximum degree delta plus 1, then Glauber dynamics mixes in n log n steps. Okay. There's a slight technicality, which is why I put the double asterisk there. Basically, Glauber dynamics technically is ergodic only if q is at least delta plus 2. But there's a very simple modification to the dynamics, which conjecturally works down to delta plus 1. But I don't want to get into many details there. Okay. So this is the conjecture. And sort of one motivation for this conjecture, and also one of sort of the interesting aspects of this sampling graph colorings, is that it exhibits what physicists call a phase transition. Okay. Actually, so before I get there, I also want to mention that sort of this conjecture has received quite a lot of attention, even for this special case of lattices. So one of the sort of interesting sort of aspects or sort of features of this model is that it exhibits what physicists call a phase transition. Okay, so in particular, it is now known that if the number of colors is less than or equal to delta, the maximum degree, then actually the problem of sampling is NP hard, even if the underlying graph is triangle-free and regular. Okay, so not only does Glauber dynamics not mix in polynomial time, but actually, under standard complexity theoretic hypotheses, there are no polynomial time algorithms whatsoever. Okay? And sort of Jerrum's conjecture sort of furnishes the other side of this transition. Okay, so it says that as long as you're above delta plus 1, you have linear time algorithms. So this really is sort of a very sharp computational phase transition where you go from sort of super polynomial time algorithms and NP hardness all of a sudden down to linear time algorithms. Okay. But unfortunately, sort of the current state of the art for fast mixing is stuck at sort of some constant times the maximum degree. And the current constant is roughly 1.8-ish. And so there's this gap between the conjectured phase transition point and the current state of the art, in which currently there's no polynomial time algorithm known for sampling graph colorings. Okay. So with my collaborators, Zhongshen, Ankur, and Nitya, we managed to almost resolve this conjecture, subject to an additional slightly technical condition, namely that the girth of the graph G, recall that the girth is sort of the length of the smallest cycle in the graph. So the condition is that the girth of this graph is at least some constant, which depends only on the maximum degree delta and the number of colors q. Okay? So notably, I want to emphasize that sort of this girth does not depend on the number of vertices of the graph. So it really is just like some constant. Okay. The theorem is that as long as Q is at least delta plus 3, which is very, very close to delta plus 1, and the girth is at least some constant, then Glauber dynamics mixes in n log n time. And just to give you a sense of sort of how large this girth requirement is, if I give you slightly more colors, 1 plus epsilon times delta many colors, where epsilon is a constant, then the girth scales roughly as 1 over epsilon squared times log of delta. So really the dependence on the maximum degree is quite mild. And of course, it remains an open question to remove these girth assumptions. But basically, if you have mild girth assumptions, then the conjecture is resolved. Now you might be wondering, sort of, where does this threshold delta plus 1 come from? Now, if you have sort of if you've seen a little bit of combinatorial optimization, or you have a theoretical computer science background, then you know that this threshold delta plus 1 comes up in analyzing sort of the local greedy algorithm for finding colorings. Okay, so the greedy algorithm is the one that sort of just sequentially colors vertices with available colors in a greedy fashion. Okay, and it is local in the sense that to color the next vertex, you just have to look at the colors already assigned to its neighbors. Okay. So this threshold delta plus 1 is precisely the threshold at which you can find a coloring using this sort of local greedy algorithm. But actually, there's sort of a deeper reason for why this delta plus 1 threshold is the right threshold. And it comes from statistical physics. Okay. So physicists have this sort of heuristic for studying these types of systems, like colorings, called belief propagation, which I won't define formally, but because we won't need it for our purposes. Okay, so this is just heuristic for studying spin systems or locally interacting particle systems like colorings. And it turns out belief propagation, this heuristic, predicts that, at least for the case of trees, when your underlying graph is a tree of maximum degree delta, so-called correlations decay rapidly if the number of colors Q is at least delta plus 1. So informally, what I mean by correlations decaying rapidly is the following. If I look at two vertices in the tree, U and V, if I look at so each of them receives a random coloring, right? And the claim is that if the number of colors is at least delta plus 1, then the correlations between these two random colors is going to be exponentially small in the distance between these two vertices. And I'll be more precise about what I mean by this later in the talk. Okay, but that's roughly what I mean by correlation decay. So just to summarize sort of the statistical physics reason for this threshold is that belief propagation, this physicist heuristic, predicts that a certain nice property of the distribution holds if the number of colors is at least delta plus 1, at least in the special case of trees. Okay. And so this sort of suggests a much broader sort of meta question, which I find extremely tantalizing, which asks the following question, so do the analytic properties of this belief propagation heuristic sort of govern computational tractability for sampling? Okay. Also, when does it accurately predict computational phase transitions? And this meta question has also received a lot of attention in the literature, and it's been an answer to it is yes is known to be yes, at least for simpler models like the antiferromagnetic easing model and for independent sets. But this remains open for more complex models like colorings. Now, sort of more combinatorial way of stating this meta question is sort of, can we reduce algorithmic sampling questions for the case of general graphs to structural properties of the distribution in the special case of trees? Okay. And the answer to this is a resounding yes in the special case where the number of colors is 2. Okay. So for models like independent sets and the easing model. Okay. But again, this question remains open for colorings. And so the broader, more general theorem that we were able to prove is the following. Suppose correlations decay exponentially fast in the special case of trees. Then for graphs of sufficiently large constant girth, at least say log of delta, Glauber dynamics mixes in n log n steps. Okay, so basically we resolve this meta question in full generality, at least in the large constant girth regime. So this theorem reduces the question of Glauber dynamics mixing on large girth graphs to establishing correlation decay for the special case of trees. Okay, so now we have to establish correlation decay for trees. And this is what we do for colorings as well. Okay, so what we showed is that if the number of colors is at least delta plus 3, then the uniform distribution over proper colorings on a tree of maximum degree delta exhibits exponentially decaying correlations. Okay. So this kind of a result was known just for the special case of the symmetric delta Airy tree using a very complex sort of computer-assisted proof from like 20 years ago or so. And the previous best such result required significantly more colors. Okay. And I guess I won't have time to get into these, but sort of the spectral independence framework has really opened the floodgates to a bunch of other applications. For instance, to sampling solutions to constraint satisfaction problems, to average case sampling problems like spin glasses, to establishing concentration inequalities, and so on, which I won't have time to discuss in this talk. Okay, so that was just sort of a sample of applications. And now I want to tell you about what is this spectral independence framework. Okay. So to define spectral independence, I need to first define for you a notion of influence or correlation between vertices in the graph. So let mu be my distribution over, let's say, colorings. Okay. I'm going to define sort of the influence of a vertex R on another vertex V as sort of the total variation distance between these two distributions, namely the distribution of the marginal distribution for a random coloring of the vertex V, conditioned on knowing that the vertex R is some color B. And I'm going to compare that conditional marginal distribution with another conditional marginal distribution, where I instead fix the color of the vertex R to, let's say, C, some other color C. Okay? So this is a kind of influence of the vertex R on the vertex V, because this quantity is really capturing how much does knowing the color assigned to the vertex R sort of influence or affect the marginal distribution for the color of the vertex V. Okay. Now we'll say our distribution is spectrally independent, eta spectrally independent, if the total influence of the vertex R is upper bounded. Okay, so, or the sum of all the influences upper bounded by some constant eta plus 1. And with the plus 1 there is sort of there for technical reasons. It's just to cancel out the case where V is equal to R in the sum on the left-hand side. So sort of one way you can interpret this bound is you're sort of upper bounding sort of some notion of distance between the distribution condition on R getting B and the distribution condition on R getting C. So maybe let's see like a couple of examples of this. So suppose I'm looking at uniform distribution over colorings of this two vertex graph, where these two vertices are connected by a single edge. So now we can sort of directly compute what these conditional marginal distributions are, right? So if I know the vertex R is colored B, then I know the vertex V cannot be colored B. And so this conditional marginal distribution is just uniform over all colors except for the color B. And similarly for C. And so you can now just directly compute sort of the total variation distance between them is going to be equal exactly to 1 over the number of colors Q minus 1. Let's see maybe a few more examples. So now suppose the distribution mu is a product measure over, say, 1 through Q to the V. Okay, so this would be the case, for instance, if the graph had no edges. So in this case, I claim that my distribution mu is going to be 0 spectrally independent. And that's just because all of these influences are going to be 0, right? If two vertices R and V, if their assignments are independent of each other, then the corresponding influence, this total variation distance, is going to be 0. Right? And so for product measures, which are sort of the nice measures for fast mixing of Markov chains, my distribution is going to be 0 spectrally independent. As a final example, sort of in the opposite extreme, if the distribution mu is, let's say, concentrated on two configurations, one of which assigns all vertices to the color B, and another which assigns color C to all the vertices, then I claim the distribution is going to be n-1 spectrally independent. And the way to see this is just that if you knew the vertex R is colored B, then you know that you're in sort of this configuration on the left, the all B configuration. And so you know that with probability 1, the vertex V is colored B as well. Right? And so in particular, all of these influences are going to be 1, the largest they can possibly be. Okay? And so in this case, we're going to have n-1 spectral independence. And you should think of this as being sort of the bad case, right? This is the case in which sort of local Markov chains are going to have a tough time sampling. Okay, so this is what spectral independence is. And now the theorem is that if I assume that my distribution mu, as well as all of its conditional distributions, are all spectrally independent, then Glauber dynamics mixes in n log n time. Okay, so you should think of eta here as being sort of a constant independent of n. Okay. So here, I just want to be very clear about what I mean by all conditional distributions. So for every subset of coordinates, and for every partial coloring on that subset of coordinates or vertices, I'm going to get a conditional distribution. And I want all exponentially many of all of these conditional distributions to all be spectrally independent. Okay, so I'm not looking for spectral independence just for mu itself, but I'm looking for spectral independence for mu as well as all of its conditional distributions. Okay. And if you have this condition, then you get polynomial time mixing of Glauber dynamics. And I want to mention that sort of since then, there have been sort of generalizations and strengthenings of the spectral independence framework that make it applicable to many other settings. Okay, so in particular, one I want to highlight is sort of this localization schemes framework of Chen and Aldon. Okay. And I also want to mention that sort of this results really built upon a sort of a beautiful and nascent theory of high-dimensional expanders, which was pioneered by these following researchers. Now, polynomial time mixing is nice, but it's not practical by any means, right? If this parameter eta is even, let's say, 3, then the first theorem would give n to the 5 mixing, which is still useless for practical applications. With Eric and Zongchen, what we managed to show is that if the distribution mu satisfies an additional structural assumption, namely that it is sort of a quote-unquote graphical model, okay? This is an assumption that is satisfied, for instance, by proper colorings. Then actually spectral independence not only implies polynomial time mixing, but actually implies n log n time mixing, which is optimal. So let me just explain sort of very briefly at a high level what I mean by the distribution mu being a graphical model. Basically, I just want the distribution to be a distribution over assignments of colors to some graph, or to the vertices of some graph. And I want this distribution to satisfy the following conditional independence property. Namely that if I partition the vertices into 3 sets, A, S, and B, such that the set S sort of separates the vertices of A from the vertices of B. Okay, more precisely, any path from a vertex in A to a vertex in B must go through a vertex in S. Then the assignment on A is going to be independent of the assignment on B condition on any assignment of the separating set S. Okay, so this is a conditional independence property which is satisfied by many models like colorings, independent sets, and so on, the Ising model, and so on. So now let me sort of explain very briefly sort of a little bit of intuition for why these theorems hold. Okay, so at a very, very high level, spectral independence for all conditional distributions roughly means that the distribution mu sort of looks like a product measure at all scales, at least from the perspective of correlations. And fast mixing for product measures is well known. But perhaps sort of another, maybe more fruitful way of getting intuition is sort of to go via the contrapositive. Okay? So imagine sort of the opposite scenario, where I have a slow mixing Markov chain, where my distribution looks like it's going to concentrate on its mass on, like, let's say, two far away configurations. Let's say the all -1 configuration and all +1 configuration. And let's say it's a small probability mass in between. So this is sort of the classic sort of bimodal landscape that's going to be very difficult for Markov chains to navigate. Now, in this case, so I guess sort of this model, this kind of distribution arises very naturally in many applications, such as, this is the case, for instance, for the so-called ferromagnetic Ising model, at least in the low temperature regime. Now, I claim that if your distribution looks like this, then its spectral independence parameter kind of must be bad, must be large, let's say linear in N. Okay, basically, the intuition is just the following. Imagine, you receive a sample from this distribution, right? And you are told that, let's say the assignment for coordinate R or the vertex R is, let's say, +1. Okay. And you're asked sort of to guess what you think the assignment was for all the remaining coordinates. Okay. Then it will be natural to guess that, you're in, because, you know the coordinate R is assigned +1, then you're more likely to be in sort of the second sort of bump in this distribution, right? And therefore, it's natural to guess that most of the other coordinates are going to be a +1 as well. And so this sort of is an informal way of, saying that, this spectral independence parameter must be large, must be at least linear in N. Okay, so this is sort of the contrapositive way of reasoning or getting an intuition on why spectral independence implies fast mixing. Okay, so we have this notion of spectral independence. This is a property of the underlying stationary distribution of the Markov chain. Okay, but where do we go from here, right? We need tools to establish this property. Okay. And so by now, there's sort of four major classes of techniques for establishing spectral independence. The first of which sort of comes from classical statistical physics, namely the correlation decay method. A second class of methods sort of comes from this idea of disagreement percolation, which is actually related to correlation decay and also related to sort of coupling distributions. A third class of techniques is based on sort of the geometry of polynomials and sort of their analytic properties, like the locations of their zeros and so on. And the fourth and final class of methods sort of come from sort of measure decompositions. Okay, so these include techniques such as the famous trickle-down method from the theory of high-dimensional expanders, but also includes methods based on, for instance, coupling Markov chains, and also certain sort of discrete to continuous principles. So I won't have time to tell you about sort of all these different techniques. But in the rest of this talk, I'm going to focus on just one in particular, namely the correlation decay method, as it is particularly relevant to our study of proper colorings. Okay, so in the remainder of the talk, I want to sort of just sketch the analysis of spectral independence for the special case of graph colorings. Okay, so just to refresh your memory, so Coloring is, again, an assignment of colors to the vertices of a graph such that neighboring vertices do not receive the same color. And our goal is to sample a uniformly random such coloring. Okay? And the theorem is that as long as Q is at least delta plus 3 and the girth of the graph is sufficiently large, then Glauber dynamics mixes in n log n time. Okay? So what we'll actually prove is that as long as the girth is at least some constant and Q is at least delta plus 3, sort of the distribution over the uniform distribution over proper colorings is spectrally independent. Okay? So this total influence is going to be upper bounded by some constant depending only on the maximum degree delta and the number of colors Q. Okay? So here's sort of like the sketch of how this argument roughly goes. Okay? So we want to do something like fast mixing. We saw earlier how this can be obtained by establishing spectral independence. We're going to first reduce the spectral independence bound to bounding correlations within small balls in the graph. This is particularly nice because small balls around a vertex in the graph is going to be a tree because we assume the graph has large girth, sufficiently large girth. Now, within these small balls, we will then apply sort of correlation decay on trees. And this correlation decay on trees is then sort of obtained by sort of using something called contraction of leaf propagation. Okay? But I'm not going to get into that arrow in this talk. So the main focus of this talk is going to be sort of these, or the remainder of this talk is going to be sort of these two arrows on the left here. Okay. So our goal is to establish spectral independence for the uniform distribution over colorings of a large girth graph. We're going to first reduce it to bounding correlations within small balls, which are trees in this graph. And then we're going to reduce bounding these correlations in small balls to correlation decay on trees. Okay. So now let me first be more precise about what I mean by correlation decay. Okay. So correlation decay is just the following property. It says that sort of this influence between these two vertices, let's say R and V, is exponentially small in the distance between these two vertices. Okay. So in particular, so good. Okay. So roughly, so the picture is as follows, right? So imagine I have two vertices, which are neighbors of each other, right? And I know one vertex is colored red. Let's say the one on the left. Then I know the vertex on the right cannot be colored red because these two vertices are connected by an edge. And so in particular, neighboring vertices are going to have very strong influences on each other. But what you would like to say is that if these vertices are very far from each other, then knowing the color assigned to this vertex on the left here is going to have very little effect or very little influence on the color assigned to the vertex on the right, or more generally on faraway vertices. So this is the intuition that correlation decay tries to capture. And basically the claim is that sort of correlation decay is going to imply spectral independence for us. This is the arrow that we would like to deduce. And just to get a sense of sort of like why correlation decay should be relevant, imagine now we're trying to bound the spectral independence, right? We're trying to bound the sum of influences, right? Well, what I can do is I can sort of break this sum into a sum over vertices at various distance scales away from this vertex R. Now, if I know correlation decay, then I know that each of these sums is bounded by something exponentially small in the distance scale times the total number of vertices at that distance scale, right? And so in particular, I'm going to get a sum that looks like this. And if I know my underlying graph is something like a lattice, let's say Z2, then I know the number of vertices is only growing polynomially fast in the distance. And so this polynomial growth in the number of vertices is going to be completely washed away by the exponential decay of correlations, right? And so I can deduce a universal upper bound, constant upper bound on the spectral independence of the distribution. Now, of course, most graphs sort of do not have this sort of sub-exponential growth property, unlike lattices, right? But already this sort of illustrates sort of a major theme that we're gonna, or a major theme that we're gonna see later in this talk, which is sort of like there's gonna be sort of two competing effects. One is sort of the decay of some measure of influence, like correlation decay, and another is going to be sort of the growth of the number of so-called sort of susceptible vertices. Okay, and we'll actually sort of see in a moment sort of an infection process that's going to be able to capture how we're going to bound the spectral independence parameter. Okay. Basically, there are two issues now. Sort of how do you show correlation decay at all, and how do you defeat the growth of the number of vertices in the radius in a non-immutable graph, for instance, for expander graphs. Okay. So just to recall sort of the rough outline of how the proof is going to go. Again, we're trying to establish spectral dependence on large girth graphs. We're going to reduce this to correlation bounds in small balls, and then we're going to reduce this to correlation decay on trees. Okay. So the first step of the argument is we're going to sort of convert this spectral independence bound into a corresponding statement for couplings. Okay. So in particular, by sort of the classic coupling lemma, it turns out that you can reduce the problem of bounding the spectral independence by the following. Okay, I want to design a coupling of two random colorings, one of which is drawn from the distribution, conditioned on, say, some vertex R being colored red, and another coloring which is drawn from the distribution, conditioned on the vertex R being colored blue. And I want to couple these two colorings in such a way that so the expected Hamming distance between these two colorings is small. Okay? And this turns out to be an upper bound on the spectral independence parameter of the distribution. Okay. So I want to design sort of this coupled pair of colorings. So you imagine sort of the following picture. Okay? You can imagine sort of designing this coupling in sort of an iterative way, where I start from this vertex R. In the picture on the left, this vertex R is colored red. In the picture on the right, this vertex R is colored blue. Okay, so these are this is a single vertex which has a disagreement at it. And now I want to sample a coloring for the rest of the graph in such a way that sort of the expected number of disagreements between these two colorings is small, is at most a constant. And you can imagine designing this coupling iteratively. So maybe I start by coupling sort of the vertices in this one-step neighborhood of this vertex R. And this maybe generates several disagreements, maybe these three vertices, which are surrounded by this orange blob here. And then maybe I then try to couple so the two-step neighborhood of this vertex R, and the set of disagreements maybe grows slightly to this, to this orange blob here. But then hopefully after, let's say, a constant number of steps, what you might hope for is that sort of the number of disagreements have died out, in which case all the vertices sort of outside of this sort of blue blob, they're going to be able to be coupled perfectly. Okay? So the hope is that you can sort of confine your disagreements to just a small orange blob, which is like, let's say, a constant radius or constant number of steps away from this vertex R. Okay. So now let's sort of try to formalize this. Okay, so here's maybe like a first attempt to build such a coupling. Okay? So here's the theorem. So suppose sort of correlation decay holds on trees. Okay? Then I claim that for every girth G graph, and for every radius less than half of the girth, the total variation distance between the vertices on the boundary of a radius capital R ball around this root vertex R is exponentially small in this radius. Okay. basically the picture looks as follows. Okay, so right. So basically this just says that sort of if I, you know, within this ball of radius, let's say girth over 2, my graph looks like a tree. And so in particular, it turns out you can apply correlation decay plus a simple application of Bayes' theorem to say that, to prove that actually sort of the total variation distance for the distribution of the vertices along the boundary of this ball is going to be small between these two pictures. So particularly if you have this lemma, okay, this lemma which says that, you know, the total variation distance between a large radius ball is going to be small between, you know, the two pictures, one in which the vertex R is colored red and the other in which the vertex R is colored blue. Then you can design sort of this iterative coupling as follows. Okay, you can first try to couple the boundary of this ball. If you manage to successfully couple, which is sort of the good case, then you manage to successfully confine all of your disagreements to within this ball, because all the vertices outside of the ball never see the disagreement at the vertex R. Now, this is just by conditional independence. But of course, sort of the bad case is that if you fail to couple, then it could be that sort of all the vertices along the boundary of this ball are going to be disagreeing, right? And so you have no control on sort of the propagation of disagreements to vertices outside of this ball. So in sort of using this sort of naive coupling, unfortunately, sort of the growth of this number of sort of susceptible vertices is going to be it's going to win out over the decay of correlations. So what you really need is sort of a more average case or statement. Okay, so what you want to say is sort of the typical behavior of this coupling is that actually only a few vertices along the boundary of this ball are going to be disagreeing. Okay. So I guess I'm running out of time slightly. So I'm going to skip sort of the more technical statements of how to formalize what it means, how to formalize sort of this typical behavior. Maybe we can also discuss during the question session. Okay. But I want to sort of conclude with sort of some future directions for this line of research. Okay. So there's sort of still many major open problems on sort of the complexity theory of sampling, in particular to, for instance, complexity phase transitions like Jerrum's conjecture on fast mixing of Glauber dynamics for proper colorings. There are also sort of problems that sort of, at least at the moment, are believed to be of sort of intermediate complexity, such as counting and sampling independent sets in bipartite graphs. And there are also many questions on sort of average case complexities. So for instance, for random instances of the problem of, let's say on random graphs, what is the complexity of sampling? Let's say a coloring or like an independent set. Okay. So another direction that I'm interested in is sort of going beyond worst case analysis of Markov chains. And for this, I want to highlight sort of a very nice recent work due to Bryce Wong, Siddhant Mohanty, Amit Rajaraman, and David X. Wu on analyzing sort of simulated annealing. Okay. And also sort of more recent works by Gasari, Sinclair, and Bresler, Nagaraj, and Nichani. But I guess sort of one question I really like along this frontier is sort of, can we do better for sort of average case instances? And there's actually a very striking conjecture, which I really like, which is the following. So it's actually known that let's say if I consider the problem of sampling independent sets, uniformly random independent set in a graph, then it is known that if the underlying graph is D-regular and triangle-free, then the problem is NP-hard if D is at least 6, some very specific constant. But it's actually conjectured that if the graph is uniformly random, then actually for all D, Glauber dynamics mixes rapidly and actually samples a uniformly random independent set. So currently, we don't have so many tools to study conjectures like this sort of or sort of to study like sort of the average case behavior of like these sampling problems. And sort of a final direction that I want to mention is sort of understanding sort of distributions that have more global constraints. So for instance, you know, many of the problems that we studied in this talk, for instance, independent sets and coloring, so the distribution is sort of parameterized by sort of local constraints and local interactions. And so there, the theory is much more developed, but not nearly as much as known for more globally defined distributions like the random cluster model, or more rigid combinatorial structures like acyclic orientations, perfect matchings, general graphs, and so on. Okay, so these are sort of, these problems remain wide open. Okay. And then I guess, of course, last but not least, I want to mention some additional directions to sort of analyzing more complex Markov chains like the Swenson-Wang or like the event chain Monte Carlo, and also to potential applications of differential privacy. But in any case, I'll stop here. Thank you for your attention.